Okay, so quick video on titrations. First off, I'm going to talk through what a titration actually is, and then go through sort of questions that you might get asked about it. So a titration is an incredibly accurate experiment where used to work out the concentration of something. So you get, if you excuse the drawing, you get a really, really long piece of glassware with a tap on the bottom, and it's got markings up the side. And that is called a burette. You get a conical flask in the bottom, and you put the conical flask on a white tile for reasons that we'll talk about later on. White tile, and then you get a very accurate pipette, and you also need an indicator, because normally titrations are used with an acid and a base, or an acid and an alkali. So let's say, for argument's sake, we have an acid, we'll say it's HCl, and we know it is exactly, because we know the concentration of this one, it is 2 moles per decimeter cubed. So we know the concentration of it. So let's say we take 25 centimeters cubed, and we take that with the pipette, because the pipette is incredibly accurate. So then we know we have got exactly 25 centimeters cubed, and we stick that in our conical flask. And we also put in an indicator, and the indicators that we tend to use are, I don't use universal indicator, we use one called methyl orange, and universal indicator, you know, it's the one that's green when it's neutral, red if it's a strong acid, and it goes through the colours of the rainbow almost. Red for a strong acid, then yellow, then green, then blue, and then purple for a really strong alkali. But for a titration, we need something that will just change instantly. So methyl orange, when it's an acid, doesn't matter how acidic it is, even a tiny, tiny, tiny bit acidic, methyl orange is red. And then as soon as it switches across into being a base or an alkali, soon as it switches across, so exactly in an instant, it will change to be yellow. And the other indicator that we use is phenolphthalein. Sorry, I've spelled that wrong already. Right, phenolphthalein. I've missed out a H. Phenolphthalein. Phenolphthalein in an acid is colourless, so totally transparent, and in a base it's a really strong, vivid pink colour, and they will change. You add one drop and it will change straight away. So going back to our titration, I should have read this out before I started. Right. So we've got our HCl in here, and let's say we're going to use sodium hydroxide, which is our alkali, NaOH, and we put NaOH in the burette, and then we know exactly that we've got 25 centimeter cubed of HCl in here, and we know exactly what the concentration is. So indicator for this one, let's say we'll use phenolphthalein. So we've put the phenolphthalein in there too, and it's in an acid, so the phenolphthalein will be totally colourless. That's the reason we put it on the white tile, so that if it does change colour, because it's against the white background, we can see it straight away. And then so we've got this burette full of NaOH, and we look at the reading on it, and you read the burette, and let's say it says it's 70.1 centimeters cubed. And then we open the tap and we let this drip out, and it drips into there, and eventually, so one drop at a time, drip, 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 eventually it'll be enough to turn the phenolphthalein, to turn this solution from an acid. When we've added the perfect amount, it will have neutralized it. And then when it's neutralized it, the phenolphthalein, it won't be an acid anymore. We'll have added enough to shift it across into a base, and the whole thing will change and be pink immediately. And then you stop, you turn off the tap, and you look at the end of it, and let's say this has gone down to, I don't know, 20.8 centimeters cubed. So we can look at the difference between those two, take them away from each other, and then you can work out exactly the volume of NaOH that you've used. Why is this useful? Why are we bothering doing all of this at all? Well, so we knew for HCl, we knew the concentration, and we know the volume. So that means we could work out, because the concentration, it told us, it was 2 moles per decimeter cubed. We knew the volume, because it was 25 centimeters cubed. So then that would let us work out the moles of HCl. We use our chemical equation. HCl, they'll give you this in the question. HCl plus NaOH goes to H2O plus NaCl. So we've got our hydrochloric acid and sodium hydroxide. They've neutralized each other. We've managed to work out exactly how many moles of this. So we know how many moles of HCl we've got. That's really, really useful. Ding! The question, the reason we were doing all of this, we wanted to find out what the concentration of NaOH was. So if we want to know the concentration of NaOH, concentration equals moles over volume. We know the volume, 70.1 minus, we know the volume that we've used. So that one, take away that one, and that is 50.7. So we've used 50.7 centimeters cubed. We know the exact volume that we've used. Brilliant to take. So we know the volume, but we don't know the moles. And if we don't know the moles, we can't work out the concentration. But this is where this comes in really handily. Because we know the moles of HCl, we can look at our chemical equation. If you remember, scientists are really, really lazy. There should be a big one in front of there, big one in front of there. So for every 1 mole of this, it reacts with 1 mole of that. Which means, because we know the moles of HCl, we also know the moles of NaOH. Which means actually, we do know the moles of NaOH. So if we know the moles and the volume, we can work out the concentration. So going back to this, the whole reason that you do the titration is you've got the volume and a concentration of one thing that you know about, and then it lets you work out the volume of the one you don't know the concentration of, and then you can use the chemical equation to work out the thing you do know. One last sort of tip about titration is, in terms of making sure that we're really accurate with this, we normally do 3 titrations. So you do one where you do it quite quickly. So you open the tap and you let it drip out quite quickly, and then you stop it, and then that's your rough titration. And then you do it twice more, very slowly, very accurately, and you have to get those readings to within 0.1 centimeter cubed of each other, and then you take the mean and use the mean of them. Now, there's something called, and I'm going to spell this wrong, it's the meniscus. I've not written this down in a while. Right. The meniscus. You've seen this before. If you have a glass of water, and you can do this at home, when you put water in, it's not totally flat. The water, because of the surface tension, goes like that. And So that's quite pronounced when you've got your burette or your pipette and you've got your readings there and you've got your liquid in it. It's not a straight line, it's like that. And so because of titration, we want to be really accurate, and you're trying to be accurate to 1 drop. With the meniscus there, you do not take that reading, you take the reading from the bottom of the meniscus. So why do we do it 3 times? To take a mean, make sure we're accurate. Why do we use a white tile? I'll rub that out for that. Why do we use a white tile? To make it easier to see the colour change. Why can't we use the universal indicator? Because we need an indicator that will change with 1 drop, and universal indicator won't. It'll be like, oh, is it yellowy green, or is that green, or when does it stop being yellow and start being green? You can't do it. So phenolphthalein or methyl orange, it just changes instantly. And then you make sure you're really accurate because you take your measurings from the bottom of the meniscus. I'll do a separate video where I practice some titration questions, but you should have an idea of what titration actually is now. So just in summary, 1 sentence, why do we do titration? It's to work out the concentration of an unknown, of a solution. So you know the concentration of one, and you do an experiment, and it lets you work out the concentration of another one.